Now, at some point, I'm guessing by now, you might have taken my name in vain because you've had to think and all this good stuff, and you all hate to do that, and it's okay. All right? Now, let's talk big picture. So, forget about the graphs, forget about everything, okay? What did you see happening yesterday in the lab? What happened? Right, what happened? You pushed the cart. Did you include the push?
No.
No.
It hit the wall.
It hit the wall?
And it bounced back.
It bounced back. Was there a direction change?
Yes.
Did the direction change happen very quickly?
Yes.
Now, read Abbott. The direction change took place quickly, right?
Yeah.
Right? So how do you, so did it accelerate very quickly?
Yes.
How do you show a big acceleration on a velocity time graph? Shallow line, steep line. Steep line, right? So this is where your physical reality has to match your graphs. Now, so here's the easiest way to start this. I'm guessing your position time graph, I'm guessing your position time graph looks something like this, right? Now, the whole key to this is up here at the top, okay? Up here at the top, does this show the three criteria? Does it show it slowing down? Yes. Does it show it speeding up? Does it show it stopping? Now, look at this. This all happens extremely quickly, okay? This isn't like your position time graph looks like this, okay? Where it stops for a long time, you know, in other words, where that plunger is fully compressed and nature goes, ooh, do I push it back against the wall or not? Don't know, I'll think about this. Okay, what the heck, I'll go ahead and push it back, all right? Nature does not like compressed energy. It likes to move. So as soon as that spring is compressed, nature goes, well, screw this, I'm going to make this spring expand. And it's going to happen very, very quickly. Now, this should be the end of that second interval. I'm guessing maybe, let's say it's around 2.5 seconds. Okay? Whatever it is. I don't care. Say it's 2.5 seconds. So here's the first, I'm going to tell you straight up. This is the first thing I'm going to look at when I look at your velocity time graphs. Your velocity time graphs, okay, here's going to be 0 meters per second. Whatever point in time your position time graph hits a peak and changes direction, it has to be the exact same time that your velocity time graph goes through 0. Okay? So whatever time this peak is whatever time this crosses 0. Okay? The first thing I'm going to look at. The very first thing I'm going to look at. Now, here's what you all want to do. Okay? You all want to play connect the dots. Because you've got a time and a velocity here, you have a time and a velocity here, you have a time and a velocity here, and you have a time and a velocity here. And this is because for 12 years of formal education, you've been taught on graphs to play connect the dots. Okay? That's what you've been taught to do. You've not been taught to think, you've been taught to play connect the dots. And for 12 years of schooling, this is what you all want to do. You want to go from this point, and let me change that part. You want to go from here to here to here to here. Alright? This is what you all want to do, because you all like playing connect the dots. You've done it for 12 years. And if there's ever an international connect the dot competition, American kids would kick butt. Okay? You all are great at playing connect the dots. However, this is not a connect the dot competition. Now, what's wrong with this picture? Sydney, what'd you say?
It doesn't cross the x-axis at the point where your position time graph makes sense.
Yeah, this thing has more issues than most people on a Maury Profit show. Okay? First off, it doesn't cross at the same time. Okay? It doesn't. And both graphs have to show the same thing happening at the same time. But you're going with Mr. Bergkamp, I have a dot. I play connect the dots. This is what American kids do. No, you don't. So first off, it doesn't show that. Now, physically, what is happening at that point? Mr. Baker, what is happening right here?
It's when the plunger hits the wall.
When the plunger hits the wall. What happens out here at this point?
It's when the plunger leaves the wall.
Now, according to this graph, from the time that it hits to the time that it leaves, if you drew your graph like that, it looks like that took about 2 seconds. So in other words, this thing is in slow motion. The car rolls in, oh, it goes, compresses. It's kind of like this matrix thing, right? And the time slows down, right? And then it stops, and the plunger expands, and then it rolls. That would happen. No, it went bam. So you have a time interval. You tried to time how long that plunger was in contact with the wall. That's why I had you get that number. Okay? So let's say it's 0.2 seconds. Okay, whatever it is. I'm guessing it's something around 0.2. So that means from the time that it hits, you go over 0.2 seconds, that's when that line has to come down like that. Okay? Now, here's the key. Here's the key, and this is why you can't play connect the dots. The whole key to this lab are 2 points. Okay? Let me kind of clear this. So, this point where it crosses, okay, because that's when the spring is fully compressed, that's when you know the velocity is 0. Now, like for example, who timed from 1.5 to the wall? Who had that time? Daniel, you did?
Yeah.
When you stopped the stopwatch, when you were timed from 1.5 to the wall, when you stopped the stopwatch, what was the velocity of the cart? Don't make this difficult.
0.
It was 0.
Yeah.
So this is what you have to think through. You have a velocity for that interval of 1.5 to the wall. But even though you have a velocity, at the very end of that interval, what was the velocity? 0. So even though you have a point in time and a velocity, scotch that back, which is a highly technical term, scotch that point back a little bit, and then bring that line down like this. Now, who timed from the wall back to 1.5? Okay? Mr. Baker, when you started that, what was the velocity?
0.
0. So if you had wall back to 1.5, you started that thing at 0. Okay? So that's going to be this. Now think about this. Okay? When the cart is rolling back, when does it have its highest velocity? Great. When that cart is rolling back, when is it going fastest? As soon as it leaves the wall. As soon as it leaves the wall, that cart begins to slow down. Right? So, when you've got this action going, now here's what's frustrating. You're going, but I don't know that point, and I've got to play connect the dots. Welcome to science. Sometimes we have to kind of like fill in the gaps. So, bring this line down, make it meet. There's your point. Now, you want to find the area. So you got a graph that looks something like this. Here's the easiest thing to do to find this area. Treat this thing as like a rectangle, okay? In other words, kind of bring a line across where it kind of is in the middle of this line, okay? And then you're going to have your height in meters per second. Then do the same thing over here, okay? So basically, on average, work this out to be a rectangle. Read?
But if we get really technical and made it a triangle.
That's fine. If you did, that's good. Okay? Now, and then do the same thing here. Now, this is what you have to be careful on when you're doing this second one, and I see this done more often than I want to admit. What you're going to use as this length is the time from here to here. You can't use the entire time. So you have to use this time as this width. Don't go out here and let's say this is 7 seconds. Don't make this width 7 seconds. It's not. This width is only from this point to this point. Okay? Now, below that data table, there are 12 possible points. Okay? 12 points. 3 sections, 4 things that I want on each one. Make sure that you have done everything that's on there. When it hits, when it's compressing, when it's expanding, when it leaves, the sign of the velocity and the acceleration in each section, when it's speeding up and when it's slowing down. Now, when you're answering the questions, like let's say, for example, I say on number 7, does the acceleration ever change sign? If so, when? Here's the answer that I do not want. Question. Here's the answer that is completely unacceptable. At the wall. Okay? There are so many things that happen when that thing is at the wall. The plunger is hitting, it's compressing, it's stopping, the plunger is expanding. Okay? At the wall is so vague. Okay? So incredibly vague. You have to be specific when you're answering these questions. Okay? You have to be specific. Now, any other general questions? You're feeling good? Feeling better about it? Okay? Now, I'll be enough, you could look at this lab in terms of F equals MA. Okay? You can look at this whole lab in terms of this. So let's talk about that. So let's say here's the wall, here's the cart. Okay? Now most of you got the cart slowing down a little bit as it rolled. What made the cart slow down? Friction, right? Now, even though I didn't tell you this, you were all clever enough to put the wheel side down and not try and do it like this, okay? Right? Because if you did it with the wheel side up, you can still do the lab, but you'd have to push it really, really, really fast to get it into the wall and have enough velocity to make it back. Okay? So you all were clever and you did the wheel side down. And that was nice. I didn't have to tell you that. Nobody asked me, Mr. Burkamp, how do you want the cart? You know? So you were clever enough to figure that out. So, but there's a little bit of friction. Okay? Not much, but there's a little bit. So this thing starts with a certain velocity. Is velocity a vector quantity? Elijah, is velocity a vector quantity? Why? Because it has direction and magnitude. Beautiful answer. Okay? And this thing has a certain direction and a certain magnitude. Now, as it rolls towards the wall, do we change the direction of the vector? Don't make this difficult. No, it's still rolling in the same direction. It's not moving in a circle, right? It's rolling in a straight line. But what's going to happen to the velocity vector as it rolls, assuming a little bit of friction? It's going to get smaller, right? So if this was my initial velocity vector, by the time it gets here, it might be a little bit smaller, okay? So anytime, and listen to me, anytime your velocity vector changes, either in size or direction, that's an acceleration. Okay? That's it. That's an acceleration. So, even though we haven't really studied acceleration yet, we're going to next week. As a gut feeling, Danny, as a gut feeling, do you think your acceleration is in the opposite direction of your velocity or in the same direction as your velocity in this situation?
Same? Opposite?
Opposite. Because if your acceleration is in the same direction that you're going, what do you think that's going to make it do? Speed up. And if your acceleration is in the opposite direction of motion, it's going to make it slow down. So, as it's rolling, I've got this pretty small negative acceleration. Okay? And you're going, wow, I got a negative acceleration. Well, conveniently, when you look at your velocity time graph, guess what? As it's rolling in, you have a fairly small negative acceleration. Okay? Now, the cart's just rolling along, minding its own business. And all of a sudden, wham, it hits the wall. Okay? As soon as it hits the wall, what does it do? Very quickly. It accelerates, right? right? It has a big acceleration, right? Because it hits the wall. Now, when it hits the wall, oh, we've got this big, massive negative acceleration. How's that going to show up here?
Straight down.
Eliza, right? Or pretty much, okay, a little bit of a slope, right? But now I've got this small negative acceleration, which is making it slow down. I hit the wall, boom, I've got this big, massive negative acceleration, which means this velocity vector very quickly is going to shrink. Okay? It's going to get smaller and smaller and smaller and smaller and smaller very, very quickly. Now, all of a sudden, once the spring is compressed, nature goes, I don't like this spring being compressed, I'm going to make it expand. As it begins to expand, now this is the whole key to this, okay? As it begins to expand, what happens to that velocity vector? What does it do? Does it change direction?
Yes.
Which way does it point now?
Back towards reference point.
Back towards the reference point. So now, my velocity vector is pointing in this direction. Now, as the spring expands, what's it going to do to that velocity vector? Make it bigger. Okay? It's going to make it bigger and bigger and bigger. Now, Danny, at this point, the velocity vectors are getting bigger and bigger and bigger this way because it's expanding. It's getting bigger. What's the direction of my acceleration? In the same direction or in the opposite direction?
The same direction.
Same direction. Ah, look. Now, just like I had a big negative acceleration that made it slow down, now I have a big negative acceleration that's going to make it do what? Speed up. So that same acceleration which makes it slow down now makes it speed up, which is why your velocity time graph comes down like this with the exact same slope. Okay? Now, it leaves the wall. Now, as it leaves the wall and it rolls back, what happens to your velocity vectors? They get smaller. So now they're pointing in this direction, but now they're going to get smaller and smaller and smaller. Danny, what's the direction of my acceleration now? To the left or to the right?
To the left.
To the left. Ah, now, look. Before, my acceleration vectors were pointing to the right, and we made that negative. Now, my acceleration vectors are pointing to the left, and guess what? Now my acceleration vectors have a positive sign, which is why that line comes up like this. Okay? Makes sense. Now, oddly enough, we know that from the very first day you walked into this room, that force equals mass times acceleration. Is mass a vector quantity or a scalar quantity? Ryan Baker.
Scalar quantity.
Why? You're right. Why are you right?
Because it doesn't show direction.
Yeah. What's your mass? 1 kilogram. It doesn't make sense to go, oh, I have a mass of 1 kilogram pointing south. Okay? This is 1 kilogram. Now, what that means is this. This is never positive or negative. So, if I have, Paige Swanson, a negative acceleration, what does that mean about the sign of the force?
Negative force.
Yes. Now, this is going to be important. Whatever the sign of the force is whatever the sign of the acceleration is. If you have negative acceleration, you have to have a negative force. If you have positive force, you have to have a positive acceleration. Oh, look. Now, this is one of the questions. Which direction does the friction act? Look, the car's rolling this way. Which direction do you think friction is going to act? In the opposite direction of motion, right? So, if you're defining this as being positive, which you are, therefore anything acting in the opposite direction has a negative sign. Oh, if I have a negative acceleration, I have to have a negative force, which, right? Now, as it rolls back this way, what's the sign of my velocity? Negative, because it switched direction. But my acceleration is going this way, which is positive, which means I have to have a positive force. Because the force and acceleration have to have the same sign. So, not only does my velocity switch sign, guess what? My friction switches sign so that it's always in the
Opposite.
direction of
Travel.
beautiful. Got it? Good?
Fantastic.
Got it? You all see clearly now. or if this is best for you to do on a Friday before Labor Day weekend. Okay? Good? Fantastic. Are there any other questions? You want anything else clarified? Going once? Going twice? So shut that down, get that handed in. So here's how the next, today, and then Monday, Tuesday, Wednesday, Thursday are going to play out of next week. So today we're going to go over what's, and this sounds horrible, okay? The graphical addition of vectors using the tip-to-tail method. Okay? Usually if you tell people this is what you're going to teach, immediately their eyes like glaze over like a glazed donut. Okay? It's like, oh, Lord. Okay? Now, the reason that we do this, and it sounds big and complicated, and it's really not, this is an example of what you know how to do this. Okay? You just don't know that you know how to do this. This intuitively makes sense. I just have to put it into a logical framework that works. So we're going to do the graphical side of this today. Tuesday, after Labor Day weekend, we'll use trig functions, and you all can use your calculators, and life will be grand. Okay? Wednesday we'll review. Thursday is the test over this whole velocity thing. Okay? So, Riley, you look happy. So, graphical addition of vectors today, trig functions Tuesday, review Wednesday, test on Thursday. Okay? So, then we'll start acceleration. Now, this will make sense, and if you're like a person that likes to write stuff down, you can write stuff down, but this will make sense once we start going through this. But here's the basic guidelines. And the reason that I make you all draw this out with rulers and protractors is because one year I was crunched for time and I skipped this step and I went right to the trig function side of it, and the kids bombed it. Okay, I had to go back and redo this anyway. So this is something, like I said, that will make sense to you, but you have to figure out how to visualize this. And some people are better at it than others, just because of the fact you kind of got to lay this out and go, well, this is going to go to this is going to go to this, how is this all going to fit together? So the first thing we have to do is establish some guidelines. And they're fairly simple. There's only like 4 of them. First off, everything is measured from the positive x-axis, and that's going to be defined as 0 degrees. So on an x and y system, your positive x-axis is going to be 0 degrees. Okay? So if I say, hey, here's 0 degrees, everybody knows this is what I'm talking about. Okay? Positive x-axis. Now, if you're a pilot, 0 degrees is due north. In physics, when we're doing this, 0 degrees is going to be the positive x-axis. The second rule is that we measure everything counterclockwise from that positive x-axis. So if I say I'm at a 45-degree angle, 45 degrees is going to be somewhere in here. If I'm at 180, I'm going to be over here. If I'm at 270, I'm down here. So that way we're not guessing. In other words, I don't want Riley thinking, well, here's 0 degrees and I'm going to make 90 over here. Okay? This way everybody's on the exact same page. So positive x-axis, that's 0 degrees. You measure everything else around like this. Okay? Everything is measured counterclockwise. Now, when you actually begin to add vectors, and like I said, this is a situation that you already know how to do this. Basically, you add them tip to tail, which will make sense here in just a second. Hence the term tip to tail method. Now, the most important thing is what I call the RU step. Okay? RU stands for resultant, origin, out. What the whole key to this, with any vector quantity, whether it's a set of forces, whether it's an accelerations, momentum, anything that can be a vector quantity, what we're trying to do is figuring out what is the net effect of all of these vectors acting at the same time. And what we're always searching for is what's known as the resultant. The resultant is like the net effect of these forces acting on it. So just remember, it's like a kangaroo. The resultant, and this is what we're always after, this is the end step of this process, is from the origin out. Okay? That's what the RU stands for. Resultant is origin out. Now, this looks horribly daunting. Y'all are going, my God, what is he raving about? we're going to start with a simple example, okay? We're going to start with a simple example, and you all will intuitively understand this, okay? You're sitting there, there's no way I know how to do this. I will bet anybody in this room $100 that you already know how to do this. You're going, I've never studied this before. You're right, you haven't, but you understand this. Now, let me give you a simple example. So let's say we're going to have a tug of war, okay, between Reed and Graber, okay? All right, we have a tug of war. So, pick a Reed, I don't care, one of the Reeds. So, force Reed is going to be acting in this direction with a force of, I don't know, 20 newtons. Now, is force a vector quantity or a scalar quantity? It's a vector quantity, right? Okay, force is like the poster child for vector quantities, right? It has a direction and it has a magnitude, right? Now, if I just say that force Reed is 20 newtons, is that complete? Reed W. Does this give you enough information to make it a vector quantity?
Has an arrow.
No, if all you saw was the 20 newtons.
Then no.
No. Why? What haven't I given you?
Direction.
Direction. Now, this is pointing along the positive x-axis, so we're going to call that what angle? 0 degrees. So force Reed is 20 newtons at 0 degrees. Okay? Now, over here I've got force Graber. Okay? Which is going to be 30 newtons. Now, is that enough information? No. What else do I need?
Direction.
Direction. So she's going to be pulling over here, which is going to be what angle? 180 degrees. So force Graber is 30 newtons at 180 degrees. Okay? Who's going to win? Graber. By how much? Okay, congratulations. You all just did vector addition using the tip-to-tail method where you find a result. Okay? You all just did that. Okay? And you're going, wow, I didn't know I could do that. Yes. Okay, here's the deal. When you draw it like this, okay, and you are going to spend a lot of time, especially with force diagrams, drawing stuff like this. When you draw all of the forces acting from the center, this is what's known as a free body diagram. You who in engineering, you will spend a tremendous amount of time studying free body diagrams. A free body diagram, you pick a point, okay, and you draw all of the forces acting from the common center. So this is like the tug of war. Here's the flag that's in the middle of the rope. I got a force going this way of 20, I got a force going this way of 30. Okay, so drawn like this, usually it's just abbreviated FBD, okay, free body diagram. Once we get into forces, we will spend a tremendous amount of time drawing these, okay? This is not tip to tail, but what this does is that it gives me an idea of where all the forces are going to act, okay? Now, to draw this using the tip to tail method, okay, this is a free body diagram. This is not tip to tail. Here's how you draw this tip to tail. Now, you're actually going to take a ruler and you're going to set up a scale. You're going to say like maybe 1 centimeter equals a newton, okay? Or maybe, because these are such big numbers, maybe 2 centimeters equals a newton. For the love of Pete, do not measure this thing in inches, okay, in any way, shape, or form. So, you're going to pick one and you're going to draw it. So, let's draw force Reed first. So I'm going to come in here and I'm going to draw this, okay? So I've got a certain scale. Now, just because you draw it doesn't mean anything, okay? That diagram, that arrow by itself has no meaning. Now, if I come down here and I say, okay, here's force Reed, 20 newtons at 0 degrees. Now I know what I've got, okay? So the next thing is we got to deal with Graber. Now, here's the whole key to this. From the end of this, okay, from the tip of this vector, is where I now draw Graber's vector. So imagine that I could cut this out, okay, and take this vector and draw it from the end of this one. Okay? If her vector was pointing in the same direction, I would draw it out like this. If it was pointing up at 90, I would draw it from this. So you draw that first vector. This now becomes a whole new x and y coordinate system. Okay? It's like I took this vector, I drew it here. Now this becomes an x and y system. So this becomes the new origin of an x and y coordinate system. And now the same rules apply. I'm going to take and measure around 180 degrees from that positive x-axis around like this. So now I'm going to draw Graber's. And Graber, blue or yellow? Blue. Okay? So now I'm going to draw hers back like this. Okay? So I'm going to label that force Graber, which is 30 newtons at 180 degrees. Now I've got my two vectors. Now, I could have more than that. I might have 3 or 4 vectors. If Rosie was pulling up this way, I would draw Rosie's up like this. Okay? And if Sydney was pulling this way from the end of Rosie's, I draw Sydney's. Okay? This is just something simple because this is just a 2-vector system. Now, from this, now I draw my resultant. Now, where do you draw the resultant? Origin out, right? Origin out. So this is my origin. So I'm going to come in here, and I'm going to draw my resultant. We'll put that in green. Okay? I'm going to draw that pointing out like this. So my resultant goes from the origin out to wherever you end up at the end of your last vector. Now, what's the value of my resultant? Sydney, what's the value of my resultant? How much is left over? So I'm going to say my R. Okay, that's what the R stands for resultant. And typically you might put like an arrow up there to indicate that it's a vector. You don't have to, but that's typically what you do. So my resultant is 10 newtons. Now, is that enough? No. What else do I need, Courtney? And what's the direction? Well, what's the blah, blah, blah degrees? 180 degrees. So the resultant is 10 newtons at 180 degrees. Because if you just say it's 10 newtons, I don't know which direction it's pointing. But when I put the 180 degrees on it, now I know which direction that's going to go. Read.
How many of these are we going to end up with, like at the end of the year? Are we going to end up with like 16 vectors or something like that?
Oh, no. At most you maybe have 5 or 6. Yeah. No, you'll get the hang of this after like 10 of them. And then that's it. So, good so far. Now, what if they were both pulling at 30 newtons? What would my resultant be? Yeah, there wouldn't be one. Okay, there wouldn't be a resultant. So if you end up back at the origin, that's it. Boom, you're done. Okay? So, your resultant always goes from the origin. Now, here's what you do wrong. Okay, here's what you do wrong. Is that you want to draw that resultant coming in like this. And this is why this intuitively doesn't make any sense. Because it's like you're saying, Reed's pulling this way, Graber's pulling that way, but yet we're going to go in the direction of Reed. Doesn't make any sense. But if you draw it from that origin out, then it makes sense. Okay? That's why I said, you all understand how to do this. I just have to show you that you understand how to do it. Now, let's change it up a little bit. Here's a soccer ball. Okay? So, Paige is going to apply a force. So, force Paige, okay, is going to be 20 newtons at what angle? 90? I can live with that. Okay? Now, at the same time that's happening, Sydney is going to kick the ball in this direction with a force of, pick a number, Sydney. 50? 50 or 15?
50.
50. Oh, big hitter. Okay? 50 newtons. Hold on, I gotta make this vector a lot bigger than. Okay? 50 newtons. So, Paige is gonna kick this way at 20. At the same time, Sydney is gonna kick this way. 50 newtons at what angle, Sydney?
180.
180. At 180 degrees. Now, here's the deal. And again, this is a situation that you intuitively understand what is going to happen. Okay? Abby, where's that ball going to go? Somewhere up like this? Up here? Closer to Sydney or closer to Paige? Why? Beautiful. Everybody agree? Okay? You see, this is just it. You understand how this process works. Okay? You get it. Oh, the ball's going to go somewhere in between, right? And it's going to be closer to Sydney because her force vector is larger. Congratulations, you just did the tip-to-tail method. Okay? You did. And you intuitively understand it. But now we need to make sure that we figure this out. So, draw like this, what kind of diagram? Where you have all the forces acting from the center. Free body diagram. Okay? This is not tip to tail. Now, here's, and I've seen this done. You can't draw the resultant from this. Because if you try and draw the resultant from this, then you get this weird arrow coming like up like this, and you're saying, okay, Paige is going to kick the ball this way, Sydney's going to kick the ball this way, but the ball is going to go something like this. I've seen it done. Okay? But the beauty of this is that I get an idea of where it's going to go. So, you start, you pick vector. It doesn't make any difference which one you start with. Let's start with Paige. So, here's going to be Paige's vector, okay? And that's going to be 20 newtons at 90 degrees. So there's force Paige. Now, this becomes a whole new x and y coordinate system. So imagine that I'm going to take Sydney's vector, I'm going to cut it, and I'm going to put it right here on the end of Paige's. Okay? I don't draw it down here, I draw it from the end of this. Paige, pick a color.
Red.
Red. Okay? So, here's going to be Sydney's, out like this. Okay? Quite a bit bigger. Okay? Right? So, I've got for Sydney, which is going to be 50 newtons at 180 degrees. Okay? Now, where do I draw my result? Mr. Moon.
In between, at the origin,
From the origin,
out.
out. So, my resultant is going to go from, let's go yellow. Okay? Let's take green. Let's try yellow. There we go. Okay? So, here's my resultant. It's going to go from here out to here. Now, initially, we're not going to use trig functions. What you are going to do is that you are going to physically measure the length of that vector. Okay? Tuesday, we'll use trig functions. Okay? For now, you would physically measure that. So you're going to take a ruler and you would measure that and say, okay, it's going to be so many newtons. So what you've got, so your result is going to be, I don't know, let's make up a number, say it's 58 newtons. Okay? Whatever that is. Now, when you give the angle, listen to me, when you give the angle, where does any angle have to be measured from?
Positive side of the x-axis.
Positive side of the x-axis. So when you give this angle, it isn't this angle. Okay? Because if you measure that angle, it might be like, 38 degrees. Well, if you say the resultant is 58 newtons at 38 degrees, where do you think that's going to be? 38 degrees, you're going to think it's somewhere over here, right? So when you give this angle, it has to be measured all the way around from that positive x-axis. Now, flash back to math. Which quadrant is this in? Second, right? Remember, first quadrant, second quadrant, third and fourth. So in that second quadrant, the angle is going to be between what and what? 90 and 180. So I'm going to measure all the way around from here. So I'm going to take my handy dandy protractor, which I happen to have. How cool is that? Right? So I'm going to measure that around. In this case, I get 160 degrees. So I would say that's 58 newtons at 160 degrees. Read.
You say we're going to use trig. Why can't right now, instead of measuring, can we not use like Pythagorean theorem to find that third side?
Because this one happens to work out to be a right angle.
But use-
Most of them aren't going to be.
But if we do get something like that, can we use Pythagorean theorem?
Not today.
I was just wondering.
Tuesday you can. Tuesday. Okay, got this. Now, at this point, you're all thinking, wow, this is easy. They're all at like right angles or 180 degrees opposite of each other. That must be a golden rule that they all work out to be 90 or 180 degrees opposite. Oh no, oh no, oh no. So let's say that we got another soccer ball, right? And Danny's going to kick the ball with a force of 20 newtons at, I don't know, 45 degrees. Okay? Now, at the same time, Garrett's going to kick the ball, let's say with 25 newtons at, I don't know, 170 degrees. Okay? So now we've got angles that aren't right angles, and they're not all, you know, on this nice little coordinate system, and it's like, well, we can't work with just each other. Yes, I am. Okay. So, but again, even though we're not in these nice little angles, okay, Danny, roughly, where's the ball going to go?
Like in between, but kind of towards Garrett,
Okay? Why?
because he has a higher force.
Yeah, slightly higher force, 25 newtons. So you got to figure the ball is going to go somewhere in between, right? Again, you all understand this. That's the beauty of drawing this out as a free body diagram, because you can look at it and go, oh, it's going to go somewhere in between. Now, you start over with the exact same process. Now, I'm actually going to show you, this is what you're going to do. You're going to have an X and Y system. Now, some people like to use graph paper because that way you always have like this nice X and Y system. Some people get confused by all the grids and they're going to draw it out on a white piece of paper. Some people like to use just plain notebook paper. I don't care, okay? I don't care. Just pick one. So, I'm going to draw this X and Y coordinate system. So, we'll draw Danny's first, 20 newtons at 45 degrees. So I'm going to come in here, I'm going to measure 45 degrees. I'm going to have a scale, maybe 2 centimeters equal a newton, something like that. And I'm going to draw Danny's. Okay? Boom, like this. So this will be, bless you, force Danny, which is 20 newtons at 45 degrees. Okay? Now I've got this one. Now, here's what's the most vital thing. Okay? This end right here, okay, right here, now becomes the new X and Y system. It's like, this just got me to a new, completely new X and Y coordinate system. So, when I measure Garrett's 25 newtons at 170, I'm not going to measure 170 like from Danny's vector. Okay? That isn't where I'm going to measure from. It's like I'm starting completely over from scratch. Okay? Completely over from scratch. I'm going to measure over here 170 degrees. Okay? And then I'm going to draw that vector, okay? And I'll make it a little longer, okay? So that's what I've got. So here's forced standing. This became a whole new x and y coordinate system. I'm going to measure around here, 170 degrees, and draw that vector. Got it? Now, so here we got force Garrett, 25 newtons at 170 degrees, okay? Whatever that is. Now, I'm going to draw my resultant, okay? David, where am I going to draw my resultant from?
From the red one to the end of the blue one?
Here?
Yes.
Out, right?
Yeah.
You always draw it from the origin out. So, I would come in here, and we'll change the color. I like that word. Okay? Oh, come on, there we go. Now, when I measure the resultant, okay, I'm not going to measure this angle. That isn't the angle I want. Which angle do I want? Courtney? Yeah, as far as the length goes, but as far as the angle goes.
Of the green line?
Yes.
Okay.
Where am I going to measure the green line angle? From where? From what point? From this point to here?
From 0 to the green line.
That original 0 degree line, right? So I'm going to measure from this original 0 degree line out to here. So in that case, if this was the scale and I did everything right, that's going to be like 128 degrees. So this would be, I don't know, maybe 35 newtons at 128 degrees. Whatever it is. Okay? Now, here's another way. Some people like this visual. Displacement is a vector quantity. So visualize this. David started here, okay? And he walked 20 steps at 45 degrees. He stopped. Then he walked 25 steps at 170 degrees. Okay? Now, Ryan needs to get to him to give him his calculator because he left it at his desk. And it's like, oh, come on, David, you got to use the trig function. You don't have a calculator. I'm going to be a mate and get your calculator. So, what this represents is the distance and the direction that Mr. Baker would have to walk to get to where David is at the end. Okay? So if you imagine walking here, stopping, turning here, but if Mr. Baker is going to go from where David started to where David ended up, this is the path that he would have to take to get there. So some people like to visualize it in terms of like walking. Okay? I don't care how you visualize it, but this is a situation that you know how to do this. I just got to force you to think it through. Okay, now stop that for just a second. Now, let me kind of take you through what I want done on this. So, you're going to, all of these, except for number 11, are going to deal with 5 vectors and 5 vectors only. Vector A, B, C, D, and E. So, to make this simple, I just gave you like a length. So vector A is 5 centimeters at 0, C is 4 centimeters at 120, da 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 da. So here are the easiest 5 points you were ever going to draw, you're ever going to earn in this class. First thing I want you to do is simply to draw these vectors. If you want to draw them all from like a common center and draw, vector A, which is 5 centimeters at 0, okay, come out here and draw this, and then you can draw BC. The reason I'm going to have you do that is that way you can visualize them when you start to add them together later on. If I don't do that, y'all tend to screw this up, and it's just frustrating. So this is going to save you some time later on, because then you'll be able to visualize where all these are going to be. So you can either draw them like separately, you can draw each vector separately, you can draw them all from the same center. I don't care, okay? But make sure they are labeled and drawn to the correct length. Now, let me give you a word of advice. If you're going to draw a vector A 5 centimeters at 0 degrees, this is not 5 little grids on your graph paper. Okay? This is an actual 5 centimeters. You are going to measure out exactly 5 centimeters. When you measure out the 5 centimeters, okay, you're going to make a mark, okay? When you draw the arrowhead, if this is 5 centimeters long, don't put the arrowhead on the end of the 5 centimeters, okay? The 5 centimeters is that, if that's where 5 centimeters is, then that's where the arrowhead. Don't put the arrowhead on the end of the 5 centimeters. This is all about precision. Okay? You need a very, very sharp pencil and an even sharper mind. Okay? Sloppiness is bad. This is all about precise lines and measuring everything exact. Now, we're going to do the first one together. Make sure that this is exactly how I want this done. So on number 2, I tell you that I want to add vector A to vector A. It's pretty simple. This is as easy as it gets. So on number 2, here's what you're going to do. You're going to draw vector A, okay, 5 centimeters at 0 degrees. Then from the end of vector A, I'm going to add another vector A. Okay? Sometimes you see this written as 2A, means the same thing. Okay? 2A or A plus A, it's the exact same thing. So you're going to draw this out. Okay? What are we going to draw the resultant? From the origin out. So a resultant is going to start here. I'll change that color a little bit, make that red. So my result is going to go from the origin out to wherever I end up. So what's the length of the origin? Or excuse me, what's the length of the resultant? At 0 degrees. So this is going to be my result. You always want to label the resultant. So here's what you're going to have. Either you can do this on the back side, you can do it on another sheet of paper. But visualize this from my standpoint. You're going to end up drawing like 11 different things. I want this clearly labeled. I want to say, okay, here's number 2. Okay, this is just going to be number 2. I should be able to look and clearly see and find number 2. This is where this is what this is going to look like. But what I want on that line beside A plus A, the only thing I want written on that line that's beside A plus A is the value of the resultant. So where it says A plus A, you're going to write 10 centimeters at 0 degrees. So where it says A plus A, that's what I want right there. So the drawing is going to be someplace else, on the back side, on a sheet of graph paper, someplace else. So what I want to be able to do, this is a sequence that's going to happen when I grade this. I'm going to go down this list, okay, and I'm going to see the only thing I want is the results. Then I'm going to flip through it, and I want to be able to see, here's number 2, here's number 3, 4, 5, 6, where everything matches up. Label the vectors, label the resultants, draw precisely, okay, keep a sharp pencil, measure precisely, should be okay. Any questions? I'm done. You're on your own. So Garrett, shut her down.